Hey, welcome back. Today, we're diving into a paper that kind of flips the script on a huge trend in AI. The whole bigger is better thing. Well, what if we could build models that are smarter instead of just bigger? This paper introduces something called the Universal Reasoning Model, and it's a really cool look at how AI can reason with more intelligence, not just more raw power. Okay, let's get into it. So here's the central mystery, right? We've got these absolutely massive AI models that can write incredible poetry. They can generate mind-blowing art. But then you give them a task that needs abstract step-by-step thinking, like the puzzles you'd find on an IQ test, and they just stumble. This is the exact problem these researchers were trying to crack. Why doesn't just adding more and more power make an AI better at reasoning? Well, it really boils down to two totally different ways of thinking about it. On one side, you have the brute force method. That's your standard transformer. Think of it like trying to build a skyscraper by designing 100 completely different, unique floors. It's huge, it's complicated. But then you have this other idea, smart repetition. That's the logic behind universal transformers. This is more like designing one single brilliant master floor plan and just reusing it 100 times. It's elegant, it's efficient, and as we're about to see, it is way more powerful. All right, so let's dig into the specifics of the problem. That whole brute force approach, while it can be powerful for certain things, comes with a seriously high price tag when you're talking about deep, complex reasoning. See, with standard AIs, their thinking power and their cost are, as the paper says, rigidly coupled. What that means is, the only way to make the model think deeper is to literally add more layers to its structure. Every single new layer adds more parameters you have to train, which directly jacks up the computing cost. So you want the model to reason twice as deep, you've pretty much got to pay twice as much. It's a strategy that gets incredibly expensive, fast. The researchers behind this paper had a hunch there was a better way, so they started digging into what actually makes a model good at reasoning. And what they found was that the secret sauce wasn't about adding more stuff, but about focusing on two core ideas that are often, believe it or not, kind of overlooked. Okay, ingredient number one is recurrent computation. This is a total game changer. So instead of information just flowing straight through a big stack of layers one time, recurrence lets the model loop back and reprocess the information over and over. It's like how you'd solve a really tough math problem, right? You don't just glance at it once. You apply a rule, you check your work, you apply it again, and you keep refining your answer with each loop. It's basically the AI equivalent of mulling something over. And the second ingredient is nonlinearity. Now, if recurrence is the process of thinking, you can think of nonlinearity as what gives that thinking its power. Here's a way to picture it. Linear relationships are simple, they're predictable, like a straight line on a graph. But the real world, and especially complex puzzles, are full of messy, unpredictable, non-linear relationships. So nonlinearity is the engine that lets an AI actually understand all that complexity and see the tricky patterns that a simpler model would just completely miss. And this quote from the paper just nails it. That fancy term, recurrent inductive bias, just means that by building the model to think in loops, you're giving it a natural advantage for solving problems step by step. The researchers realized that this, plus a powerful nonlinear engine to handle the messy parts, is where the real reasoning magic happens. It wasn't about some brand new, crazy architecture, but about using these basic ideas in a much smarter way. So, with this insight in their back pocket, the team went to work building a new model that really maxed out these two principles. And the result is the Universal Reasoning Model, or URM. It's basically a supercharged, upgraded version of the Universal Transformer. They made two really important upgrades to create the URM. First, they added a component called conswaglu. Now, don't worry about the crazy name. What it does is act like a magnifying glass. It helps the model pay super close attention to how nearby words or puzzle pieces are related, which really boosts its ability to spot local patterns. And second, they used a much smarter way for the model to learn. And this analogy for that learning technique is just perfect. When the model is learning from its mistakes over all those thinking loops, trying to send corrections all the way back to the very first step can get really messy and inefficient. So this technique basically tells the model, hey, just focus on fixing the mistakes you made in the last few loops. It makes the whole learning process way more stable and a lot more effective. So here's the bottom line. Here's how different this thing looks. A standard transformer, it's a big, rigid stack of unique layers. But the URM? It's a small, super efficient set of layers that get reused over and over again in a loop. And because of that clever learning trick we just talked about, it can even dedicate some of its thinking loops to just processing and other loops to both processing and learning. It's incredibly flexible. Okay, so the theory sounds great, it's elegant, but does it actually work? Well, the researchers threw it up against some of the absolute hardest AI reasoning tests out there. And honestly, the results are pretty staggering. This number is the big headline, 53.8%. That is the URM's brand new state-of-the-art accuracy on a crazy difficult test of abstract reasoning called ARC-AGI-1. What that means is on its very first try, it gets the puzzle right more than half the time. That's a huge deal. And as you can see right here on this chart, that number isn't just a little improvement. The URM there on the far left is just blowing the previous leading models out of the water. This isn't just a step forward, it's a genuine leap in how AIs can reason. And it wasn't just a one-hit wonder either. On an even harder version of the test, it nearly tripled the performance of the older models. And just for fun, they tested it on Sudoku, where it also beat out all the competition. This really proves that the URM's approach is solid across all kinds of different reasoning tasks. But here it is. Here's what I think is the most important part of this whole story. The performance is incredible, yes, but the truly game-changing discovery is how the URM gets these results, with just stunning efficiency. You have to look at this table. It's wild. A huge standard transformer with 32 times the parameters barely squeaks by with a 24% score. But then you have a universal transformer, the foundation for the URM, with only 4 times the parameters, and it hits a 40% score. It is doing so much more with so much less. And that really brings us to the core message of this entire paper. When it comes to complex reasoning, just throwing brute force at the problem is not the answer. The architecture, the ability to think iteratively, to think deeply, is so much more important than just the raw size of the model. Smart repetition beats brute force, hands down. So why does any of this matter in the real world? Well, the implications are absolutely huge. Smaller, more efficient models mean you don't need a giant data center to run powerful AI. It could run on cheaper hardware, maybe even on your own local device one day. They're faster and cheaper to train, which just speeds up innovation. And maybe most importantly, this opens the door to creating super powerful, specialized AIs for specific jobs, like financial modeling or drug discovery, without needing a giant one-size-fits-all model. You know, research like this forces us to ask a really big question. For years, the race has been all about building one single giant AI brain. But papers like this suggest a totally different future might be on the horizon, a future that isn't filled with a single giant AGI, but with millions of small, efficient, and brilliantly specialized AIs, each one a master of its own little world, a future that's smarter, not just bigger.